Okay, so today we shall start next chapter, gas turbine power plant. This is what we briefly already covered in Thermo 2. So would remember something.
Previous sections, and so that guaranteed the 4 p.m.
So, so this chapter, of course, covered from Eunice Angel, but I'm also using this second book also, McConkie, because I do not want you to waste time to go through those tables. So in McConkie, there is a short, easy way to do it. So I will explain it. So let's start without wasting any time. So gas turbine power plant, just like steam power plant, is based on Rankine cycle. So gas turbine power plant is based on this Britten cycle proposed by this person in 1870. Right, the same four processes, but now the working fluid is throughout a gas. There is no boiling or condensation like in steam power plant. So it's the normal air, ambient air is first compressed, then it is burnt with fuel. We get high temperature mixture of gases which enter into a turbine and we get work output. But here we are compressing a gas, not liquid. So here VDP product is, which is the work that is much, much bigger. Right.
That's the small 8.2.
Yeah. Whatever you will say, it will right here. I need to come out of it. I don't know which. Okay, this one. So this is the major issue here, that the work of compressor is much bigger than work of pump in equivalent steam power plant. So that's why a large amount of this turbine work goes back and reused in the compressor. Okay. So here to get the same amount of power, we have to use a large M dot here to get the same amount of work, because a significant work is being used again in the compressor. Normally, it is not recirculated because it is not the same gas. Like in steam power plant, it is the same fluid, which was water, which we can reuse after rejecting heat. Okay, but here we cannot reuse it. It goes into the ambient and the fresh air enters here. So the exhaust process is just a waste of gases into the ambient. And from the ambient, we get it back again.
So only
Yeah, only turbine work. There is no other source except this turbine work. Okay, so yeah.
I think that there is all derivatives.
Yes, those can be used, but here we are talking about the simplest type of Britten cycle. So those things will come later because here temperature are still very high, so we can use it. This is an open cycle because air is entering into the system and going into the ambient back. That's why it is also an open cycle. And here you see two different types of gas turbine cycles. This is the reciprocating type, and this is a rotary type. So here we are using rotary compressors, rotary turbine. Here we have reciprocating type of compressor, reciprocating type of, we can also say it's a turbine because it is producing water. But this chapter is all about this type of gas turbine power plant. This is separate. This is a diesel engine power plant. Okay. Uh, the same four processes: compression, combustion, expansion, and then finally exhaust. But it is operating in two different ways. Here, this type of machine is called rotodynamic machine. And this type of machine is called positive displacement machine. The analysis of both of these machines are different, right? Because here the fluid flow is continuous. Here the fluid flow is not continuous, it's pulsating or intermittent. Okay, so but this chapter is all about this type of gas turbine, which are used not only to produce electrical energy, but also to produce mechanical work for jet engines, right? And also rocket engines. Okay, let's move on. So here is the same schematic. Now these are the uh, theoretical part, which you can go through by yourself. Here, the maximum temperature in the combustion chamber, it may reach up to 1200 degrees Celsius or even more. Actually, we have to control this temperature because this temperature will be very high when we directly combusting the gas. Here you also see nozzle, which is supplying that fuel at a higher velocity to this air, and this air fuel mixture gets burned directly here. So this direct combustion, and then those gases are actually used to run this turbine. There is no another fluid like in steam power plant. This combustion is taking place separate, and heat is transferred to the steam. Okay. So the commonly used fuels, the most common one is of course natural gas, which are used in these gas turbine power plants. The overall efficiency is given. Then we can also use diesel in such power plants, not only for diesel engines, reciprocating type, also for this type of engines, diesel can also be used. Okay, for remote areas where natural gas is not available. Anyways, the rest. And of course, in jet engines, the fuel is also liquid fuel, but of different composition. So those are called kerosene or JP4, JP8. So, but the overall operation is the same: compression, combustion chamber, and expansion. This is another type of gas which can be used in these gas turbine power plants if we can convert coal into gas form. Not solid coal, but gaseous coal. There is a chemical process which can convert this solid coal into a gas form. So that gas can be used, or we can also use biomass. So this is named as sign gas. If we convert coal or we use biomass to run that gas turbine power plant. So these are the commonly used fuels. The most common one is, of course, natural gas. Okay. Advantages compared to steam power plant, of course, no warm up time. They can start quickly and immediately. There is no need to produce steam from so a large amount of water. So they can start quickly. That's why these power plants are used for peak load, because they can start quickly and they reach the steady state quickly. Here in this graph, you see a closed cycle gas power plant. This one is open cycle, but this one here it's a closed cycle. Here we are burning a gas, the same fuel, but it is transferring heat to another gas. And the other gas is flowing through this turbine. You are cooling this gas and then it is compressed and then, but it's not very common. For example, here we can use helium. Here, air plus fuel mixture, and it is giving its heat to another fluid. For example, helium or CO2 is also used. Helium is lighter. Helium is lighter means its K value, this Cp over Cv, is different from air. And we shall see the effect of this K later on, right? So that from helium, we can get higher efficiency, higher network output compared to air. But this is more expensive because here you have extra heat exchanger, more unusual fluid, right, which is not easily available. And of course, we can also use CO2 in some gas power plants. They also use CO2 as a working substance. CO2 has major advantages that it is more dense than helium. So you need less mass flow rate to produce the same amount of power because it is much more dense than helium. But these closed cycle gas power plants, they are not as successful as open cycle because in open cycle, we are using normal freely available air. Okay. But though there are few plants available in the world, one in Japan and one in Germany, where they are using, but those are only used for experimental purpose. Those do not prove to be as economical as the open cycle. It could be a closed cycle, but closed cycle means now you have a second working fluid, right? Air and fuel is burning.
Yes, the point of hands are open or closed.
Both.
Oh,
In the previous slide, we saw open.
okay.
Air is entering, air is burning, air is leaving. Here, air is burning, and the heat is transferred to another fluid which is flowing in that cycle. And that other fluid I just explained, helium or CO2. And that is closed. Helium is not going into the ambient, it is cooled here. Helium is not changing its chemical composition. Which power plant, open or closed? Open. Yeah, they have exhaust. If it is open cycle, if it is closed cycle, even then there is exhaust, but there are this exhaust separate. Okay, in fluid is circulating, that's why it is closed. Closed means fluid is circulating. Okay. Okay, they are compact, like, okay, that just go through these maximum temperature which we can obtain at the inlet of turbine is around 1300 degrees Celsius. In case of steam power plant, it was restricted to 600, but here we can have higher temperature, but pressures are much lower than steam power plants. Okay, but that's why here the turbine blades are of different material than steam power plants, which can sustain such high temperatures. Okay. They can be paired with steam cycle because at the exhaust, the temperature is much higher, which can be used to produce steam. Right. Okay, here as such, no cooling water, as much cooling water required as in the steam power plant, because in the steam power plant, we have a complete condenser cooling tower procedures, but here there is no such thing. Okay, no ash disposable because normal the fuel which is used that is combusted and exhausted. Right? But the fuel is not coal here, solid coal. In case of solid coal, which is used in steam power plant, it becomes ash and then it has to be removed also. Okay, let's just go through it. Cogeneration, of course, we can use these exhaust gases for another. Okay, low capital cost compared to equivalent steam power plant. In the steam power plant, the major issue is these condenser and cooling towers, which are not existing here. That's why the overall cost is low. Disadvantages, they are not good if the load is continuously varying. They are best if the load is constant.
Load what?
Load of generator. Generator means the load of consumer, right? If that load is varying a lot, then their efficiency drops compared to the other power plants. So they have low part load efficiency. Highly sensitive to component efficiency because here compressor is taking a lot of work from the turbine. So the compressor efficiency becomes very important here, not as much as the pump efficiency in steam power, right? Because pump power is already very low. So here they are highly sensitive to component efficiencies, both compressor and turbine. High air rate needed because here in the direct combustion, if you remember from Thermo 2 in combustion chapter, when you burn a fuel with theoretical amount of air, do you remember what was theoretical amount of air or stoichiometric air?
Excess air in order for the combustion to be completed. So
Not excess air. enough amount of air which will make the combustion complete. That is called theoretical air. But that will give us very high temperature, more than 2000. That's why we use excess air, so that this temperature should not go too high in 2000 plus. So that's why in gas power plant, we use extra air, excess air. Small amount of air is used for combustion. The other is not combusting. They are just decreasing the temperature to our desired level, which we need normally here around 1000 degrees Celsius. Okay. So here, the amount of air which is used in the combustion is much, much bigger. High compressor work, of course, that is clear. That's why the overall efficiency drops. Okay, high quality air and gas filters are required to prevent the erosion or corrosion of blades. They are very much dependent upon ambient condition. If ambient temperature is already very low, very cold, so it means your combustion has to do more to raise the temperature. So ambient conditions also plays a very important role. If the same gas turbine power plant is installed in a jet engine, and a jet engine is flying at a very high altitude, so pressure is also very low. So your compressor work increases because already ambient pressure is very low. So that's why that is one of the disadvantages. They are dependent upon ambient conditions. Applications, so all these are major applications. Of course, electrical power generation, but cogeneration, we can use both for heat and power, just like in steam power plant. They're one of the major application because you never use steam power plant in aircraft. You do not want to carry condenser cooling tower with the aircraft. So that's why those are used in aviation or aircraft propulsion, marine propulsion also, gas turbine or diesel engines, both are used. This gas turbine cycle or reciprocating diesel engines. And of course, in industry, backup power supply, normally diesel engines are preferred, but those can also be used if you have natural gas available. Remote power generation. So these are major applications. Okay, just okay. So now we'll start the thermodynamic part of this gas power. So I tried to cover the first part as quickly as possible. Now we shall uh, do the thermodynamic analysis of this gas turbine power plant. Same four components, compressor. This combustion chamber is replaced with heat exchanger. If you remember, that's what we used to do if we apply air standard assumptions. Air standard assumption means I'm assuming in the entire cycle, the working fluid is air, but actually it is after combustion or during combustion, it is air plus fuel, which becomes mixture of gases. Actually, it is the case, mixture of gases. But in gas power plants, uh, here normally to burn 1 kilogram of natural gas, we need around no 15 around 10 to 15 kilograms of uh, air to burn 1 kilogram of natural gas completely. But here for gas power plants, we spend much larger amount of air. So that temperature remains under reasonable value. So here we are using one up to or more than 50 ratio. So for 1 kilogram of fuel, we are sending 50 kilograms or even more air. Okay. So when this 1 and 50 mixes, then they burn, still a major portion is still air, unburnt air. So that's why it is a good assumption if we treat the whole in the entire loop as pure air. And this combustion process is replaced with just heat addition. Whatever combustion heat we have calculated, treat it as heat addition to air. Similarly, here heat rejection is replaced with another cooling process. Okay, so exhaust gas is going into the ambient, they cool down, and we take the same air out again. So we can replace this exhaust with another heat exchanger. So this is called ideal gas turbine cycle, which is named as ideal Britten cycle. Just like Rankine cycle, here we have Britten cycle. Okay. So this is what we already covered in Thermo 2 also. So Can go through now. TS diagram. Okay, let's draw TS diagram. Now in this chapter, no need to show dome because we are entirely in the gaseous region. So starting from compression 1 to 2, isentropic compression, then 2 to 3, constant pressure, heat addition. So constant pressure in gaseous region, 3 to 4, isentropic expansion, and 4 to 1, heat rejection. This is Q out, this is Q in. This is representing work in, this is representing work out. Q in minus Q out, that represents network output. Same we can also show on PV diagram because here work of compressor is quite a lot. So PV, let's show it also on PV. Now the same 1 to 2 on PV because pressure and volume both are changing. 1 to 2 on PV. This is compression, pressure is dropped, pressure is increased, volume is dropped. What isentropic compression means PV to the power gamma is equal to constant. Okay, thermo 1, 2 of our isentropic compression or expansion PV to the power gamma. Then constant pressure, heat addition, this one, 3 to 4, another expansion, pressure is dropping, volume is increasing, isentropic PV to the power, again gamma is equal to constant, and then constant pressure, heat rejection. Now here, area under this curve 1 to 2 was 0 because there is no heat transfer. But area under this curve on PV diagram is representing what? Work input to the compressor. Then area under this 3 to 4 is representing work of turbine. This area under 3 to 4 must be bigger than area under 1 to 2. Yeah. Ideal gas, isotropic, constant specific heat, chapter 2 of thermo 2. Entropy chapter, there we derive these equations. We will be using these equations here in this chapter. Yep.
P2 over P1 to the power K minus.
Yeah, it is the same equation. So here is TS diagram, here is PV diagram. I said this is PV to the power. Gamma is equal to constant. This is also PV to the power gamma is equal to constant. Okay, but here, did you notice that slope of these curves is not same, although both have the same equation, PV to the power gamma. So yes, one of the reason is different specific heat. Yes, you are right. And different gamma also, because in actual process, it's pure air which is compressing, but here it is mixture of gases, air and fuel which was burned. Because here it is actually gases, in which major part is air. So that has an effect on gamma. Gamma for pure air is 1.4, but for these mixture of gases, gamma drops a bit. It is about 1.333 something. That's why here the value of gamma is also different. Right? Why gamma is different? Because gamma is equal to Cp over Cv, and Cp and Cv changed for these mixture. That's why you see a different slope. Okay. Now in this book of Sengel, he is treating Cp as a function of temperature. And for that, we learned again in Thermo 2 that process of evaluating these temperatures and pressure using PR and VR. There were separate tables for it. Okay. But I do not want you to use those tables. If you want, okay, it's up to you. Okay. If you, to save time, we'll follow the procedure of McConkey. What McConkey does, he uses one particular CP for this process. CP of air 1.005 for pure air, constant. And for this one, for this combustion and for turbine, is use another CP, 1 point something, 1 something, a different CP for this mixture of gases, but constant. So that you can avoid this PR, VR tables. Okay. So the practice problems of this chapter, you see both problems from Sengel and also from McConkey. So the Sengel problems you can also solve using this assumption. Your answer will be a little different. You can see the error also because the Sengel approach is more accurate because it is accounting for Cp as a function of temperature. But I'm allowing you to use constant Cp for compression and for expansion. And turbine and combustion chamber, constant Cp 1.11, and for compressor, constant Cp 1.005, or gamma is 1.4. Here gamma is 1.33. Okay. Yeah, those will be given. But if you want, I'm not stopping you. If you bring tables, bring your own tables. Not available in this book. If available, I think there will be too many lines. Maybe check at the end. The TS diagram for water is given, but not for air. Okay. So for this McConkey, I have uploaded solution yesterday. Okay, handwritten solution, very old ones. Okay. For Sengel, of course, you have the solution manual, but that solution manual is according to varying Cp. Cp as a function of temperature, which you can solve like a constant Cp. That's clear. Okay. Let's move on. So the four processes are now easy. You know the names, you can name them: ideal isentropic compression, isobaric heat addition, isentropic expansion, isobaric heat rejection. Okay. Same on PV diagram. Okay, now let's derive its efficiency equation. Heat in previous chapter, we used to call it as H3 minus H2. H3 minus H2. And we used to calculate those enthalpies directly from the tables or charts. Here, no table, no chart for air. So, but it is constant Cp. So you simply use this. So we need to calculate temperatures. Cp is given constant. So this will be Q in. What is Q out? H4 minus H1. So another Cp into T4 minus T1. So that will give me efficiency 1 minus Q out over Q in, which I can write 1 minus Cp T4 minus T1 over Cp into T3 minus T2. This Cp will cancel with this Cp if I assume constant Cp throughout, only then. No. Yeah, they will not cancel out. So then I will write efficiency in this form. Here, now I want to show efficiency in a different form, for which I am assuming constant Cp. Okay. Yes. If there is mention clearly that Cp is constant in the entire cycle, then we can use this equation, which I'm now deriving. I will derive it, or we have. Okay, okay, this is clear. Q in, Q out. Now here Cp, if I assume constant Cp, then it can be cancelled. Now we have efficiency only in terms of temperatures at 4 points, 1, 2, 3, 4. Now let's convert this equation into a form which is easy to interpret. So here T1 is taken common, here T2 is taken common. Okay, then we get this thing. Now see, this is isentropic process. This is also isentropic. So for isentropic process and for ideal gas and for constant specific heat, this was the equation, right? We never used this equation in previous chapter because it was not an ideal gas. That's why there was isentropic. And also Cp, we were not assuming constant. We were taking actual values from the table or chart. So the Cp as a function of temperature was there in those, the effect was there. But here I'm saying constant Cp, constant isentropic, and the third thing, ideal gas, ideal gas. Now here you see P2 is equal to P3. So I can replace with P2 with P3, and P1 is equal to P4. So I can write the same thing as this one. And again for isentropic, because this process is also isentropic, so I can put it equal to T3 by T4. It means this term is equal to this term. If you cross multiply, so this will give us T4 by T1 is equal to T3 by T2. If you cross multiply. So here it means this ratio are equal from this isentropic relations. It means this T4 by T1 is equal to this T3 by T2. So this whole term will cancel with each other for these three major assumptions. So what is left? Efficiency is equal to 1 minus T1 over T2. I can write it because I want to get rid of these temperatures. I want to write everything in terms of pressures. So I can write it as 1 minus 1 over T2 over T1. Okay. And T2 over T1, I can replace it with P2 over P1 to the power K minus 1 over K. So efficiency is 1 minus 1 over P2 over P1, which is called pressure ratio. The pressure which was increased in the compressor. P2 over P1 represents pressure across compressor. And that is represented by RP in this book, pressure ratio to the power K minus 1 over K. So here we have an efficiency equation. If I assume ideal gas, constant Cp, and compression and expansion are isentropic, then efficiency is only a function of pressure ratio. So now we have major parameters which are affecting the efficiency if we neglect friction and other smaller things. So these are the major parameters which are affecting the efficiency of a gas turbine cycle. Now, what are those? Pressure ratio and type of fluid, K, gamma, or K, that is Cp over Cv. The type of gas which is used here. Okay, so for this ideal cycle, here is the efficiency equation. I've explained all this. Here is this, the efficiency of theoretical Britten cycle. So here is the effect of major parameters. Now we can see the effect of these two major parameters, which we already discussed in Thermo 2. That's why I'm going a bit fast. So efficiency as a function of pressure ratio for fixed K, if K is fixed, 1.4 or gamma. Okay, so that is the curve which we will obtain. Efficiency increases with this one, with increasing pressure ratio for a fixed K. Okay, let's see what is meant by this thing here on this cycle. Increasing pressure ratio means if 0.1 is fixed, I'm increasing P2. So this 0.3 will shift here. Then for the same ambient, if ambient pressure is same. So here the network output is increased. Although heat input is also increasing, but the net effect is increasing efficiency, more network output. If you further increase this pressure ratio, this 0.2 is shifted here. So 0.3 is also will shift here. If there is no limit on maximum temperature. So then this is what is happening, that efficiencies keep on increasing by increasing pressure ratio. But again, after a certain point, this change is very small, becomes very small because heat input is also increasing, right? But here I'm saying if there is no limit on maximum temperature, but if there is a limit, there is always a limit. So if this is the maximum, we cannot go beyond this temperature. Now what will be the effect of increasing pressure ratio? Then the curve will not be like this. If you say the maximum T3 is fixed, then the curve will look like this. This is 1 to 2. And this is maximum temperature 3, which is allowed. For example, this is 1000 degrees Celsius. Here is 4, 5.
It's doesn't consider the limit.
Here, yes, it's general. When there is no fixed temperature T3, when it says fixed temperature T3, we get a different graph. So here it is not saying it is T3. So you're always looking for making people wrong. Okay. Okay. Yeah, it's very easy to ask questions. It's very difficult to give answers. They are giving answers to us. Okay. Asking question is not that difficult. Okay. So now if you increase the pressure, here is a limit. I cannot go beyond this point. So I have to come back here. So maybe again, the network input, the network output is increased. But if the pressure ratio is increased more, then this is the maximum. Then maybe this network area is not that big compared to heat transfer area. P1 is fixed, ambient. Now we are increasing P2, so that higher pressure ratio. But there is a fixed T3. So now the area, network area, it keeps on increasing. Then at a certain high pressure ratio, it starts to drop because T3 is fixed. Then this curve will have some drop after a certain pressure ratio if T3 gets fixed. That's what we will see. Here, now this graph, I took it from the other book, McConkie book. He is explaining the same thing. By fixing T maximum, now if you are increasing this pressure ratio, initially with the increasing pressure ratio, efficiency increases, but then there is a drop. For example, here you see 3 curves. If maximum temperature is 780 Kelvin, if you fix T3 to 780 Kelvin. No, K is fixed. Yeah, K is fixed, only increasing pressure ratio by keeping T3 fixed. This one. For me, it's left. Okay, here. This T here in is fixed by increasing pressure ratio. more work is sent to the compressor
My question is how you increase the percentage?
by giving more work to the compressor.
P2.
Yeah. P2 is dependent upon work of compressor which we are supplying. Okay. So for a fixed P1 and T1, if you keep on increasing P2, so it means P2 by P1 is increasing. But here, if maximum temperature is fixed to 780, then this is the curve. Initially, pressure efficiency increases, but then it starts to drop. But if I increase this limit to 1100 Kelvin, then this curve will shift here. Again, there will be a maximum point, and then it will start to drop. If you want higher efficiency, so keep on increasing this one. Now, what is this curve? No limit on T3. No limit on T3, this efficiency is increasing. Air standard assumption means constant CP, but with no fixed.
That's not a plan that the maximum temperature is fixed.
No, if then he will mention here. If nothing is mentioned, it means T3 is not fixed. Here they have mentioned. No? Look here. Here they have mentioned. Here they did not mention. So they are just plotting air standard efficiency. Okay. Okay. For these three, one more thing here. Isentropic efficiency of compressor. These X curves they have actually developed from by calculating. Okay. So here, these three curves, isentropic efficiency of compressor is given, isentropic efficiency of turbine is given. Look, if isentropic efficiency of compressor is this much, isentropic efficiency of turbine, inlet temperature is this one, just by varying T3 and pressure ratio, these are the curves which we get. And this curve, isentropic efficiency, okay, you may take isentropic efficiency. You may take isentropic efficiency, but no fixed T3. No, it will drop if you further increase the pressure because now it's getting flat, but we have to check further. Because of the limit, now this area becomes smaller than heat input, which is shown here. Okay, so initially for very low pressure, area is smaller, but for high pressure, area becomes quite big if T3 is fixed. Now this is cycle efficiency versus pressure ratio. We can also plot, instead of cycle efficiency, I can also plot W net out. If I draw another graph, not efficiency, but just W net out and as a function of pressure ratio, RP. Why not? Yeah, though, no. Efficiency is
About Q1.
Q1. And what is W net? Or W of turbine minus work of compressor. Those are a little different. Those are not exactly same. That's what they have observed. That's why the next slide is important. Here you have efficiency versus pressure ratio. If you do the same calculations, not for efficiency, but for specific work, net work output versus pressure ratio. Similar trends, but the peak points are not matching exactly. Look here, just give me a point. Here you see the maximum network output here is at this pressure ratio. But if for efficiency, a little higher pressure ratio, because both are two different terms, not exactly same terms. Efficiency is 1 minus Q out over Q in. And work of turbine is work of net work output is work of turbine minus work of compressor. Here, efficiency is telling us the difference between this maximum temperature and minimum temperature. This is it. How much of this is converted into work here? That is efficiency. But what is net work output? This minus this compressor. So by increasing pressure ratio, okay, this term here goes here. Now here, this difference increases at higher pressure ratio. Okay. If I use higher pressure ratio, efficiency increases. Why? Because here this difference is increased. Okay. But what about work ratio? Look, turbine work is increased, but at the same time, compressor work is also increasing. So that's why the peak doesn't match for both, because the both are different terms. And here you see the curves which they have drawn, not actually by calculating, by performing calculations for these three different temperatures. So peak. So that's why what should we select? So now there is a compromise. Either we should choose our power plant based on maximum network output or maximum efficiency. What pressure ratio should I choose? This one or this one? So it is a compromise between both. Yeah. But their work of compressor, it's a different thing. It's a different equation altogether. So that's why peaks doesn't match. So that's why here you see both curves. One is cycle efficiency, other is this one. Okay, if we choose higher efficiency, it means we will be getting less work output, less net work output. If I choose this pressure, then less net work output, although higher efficiency. Less network output means specific. Specific means per unit mass. So I have to multiply with a larger mass to get my required work. So larger m dot. Larger m dot, bigger turbine sizes and compressor sizes. So that's why those are taken in this. So all these calculations they have done, they have performed all those economic analysis, and they come up with this number that pressure ratio is normally chosen between this range, 11 to, this is 11 to 16. Okay. Here, maximum efficiency, but network is here maximum. So they are choosing between these two regions, 11 to 16. Air in gas turbine, we already discussed. It is performing two functions. One, to burn the fuel. Second, to keep the temperature in a reasonable value, which we want. Okay, that's why here air to fuel ratio is very high. 50 or above is very common in these gas turbine cycles. Okay. That's why here, if we are treating these combustion gases as air to keep our mathematics simple, so it will not give a very large error because of very high air to fuel ratio. Okay, so the rest hopefully you can study by yourself. Okay. Here in these gas turbine cycles, this is also another important performance parameter. One is, of course, efficiency. Second, we studied network output. The third is work ratio. Work ratio, because there is a lot of work going back to the compressor. So the net work is smaller. So that is the total work of turbine. So if you divide this work of turbine divided by this gross work is named as work ratio. Or there is another term which is called back work ratio. If you divide this compressor work with gross work, then it is called back work ratio. That is work ratio, and this is back work ratio. Here is back. So these are the two more important parameters which we normally mention in gas turbine cycles: efficiency, net work output, and back work ratio. Okay, and this back work ratio is very high in case of gas power plant because this is negligible in case of steam power plants. So that's where steam power plants, they outperform gas turbines because of their very low back work ratio. This work is negligibly small. But in steam power plants, we have other issues. Then we have huge condenser cooling towers, which is not existing here. Or combine these power plants, these two power plants. Does compressor?
What? Fine, what it?
Actually, there we are using pump. So turbine is producing electrical energy. We are using that electrical energy to derive the pump. So indirectly, yes. Okay. Now let's derive one equation. Optimum pressure ratio for net work output. See this figure again. What is that pressure ratio which will give me this maximum net work output? Or what is this pressure ratio which will give us maximum net work output at that fixed temperature T1 and T3? If T1 and T3 are fixed, what is the optimum pressure ratio which will give us highest backup? So it means slope of this curve will be 0. So that concept we'll use and we'll derive an equation. Yes, if derivation is there, yeah, it's 400 level code. So this derivation is important. Okay. I'm relaxing you from tables and charts. Derivations. Okay, let's do derivation. Isentropic. So for isentropic processes, we know, right? Come out of the shock. Derivation will be an exam. So let's focus here. So T2 by T1 is equal to P2 by P1 to the power. Similarly, T3 by T4, same P2 by P1 because P2 is equal to P3, P1 is equal to P4. This is step 1. Now I can write this equation T2 separate, T4 separate. Because after that, I will write the equation of net work output. What is net work output? Cp into T3 minus T4 minus Cp into T2 minus T1. Okay. And I want to replace T2 and T4. I want everything in terms of fixed T1 and fixed T3. If this T1 is fixed and T3 is fixed, okay, so I want a correlation in terms of T1 and T3. So I want to get rid of T2 and T4, which are not required. Depending upon the materials of turbine, you can go as high as possible, but normally the range is around 1,000 to 1,300. Yeah, if you have better materials, of course, you can go higher than this. But normally they do not go higher than this, up to my knowledge. Okay, so this step is clear. Using isentropic correlations, we have written T2 and T4 in terms of T1 and T3. And of course, pressure ratio and K minus K is 0. Now, what is the network output? That's work of compressor. And what is CP T3 minus T4? Minus T2 minus T1. Here again, I'm assuming same CP for both processes. Now replace this T4 and T2 in this equation. So that you will have an equation in terms of only T1 and T3, which are given, which are fixed. And then we shall simplify it. Here is the network output equation. So let's T4 here and T2 here. This one and this one. Okay. So once you will put here this T3 here, T3 will be common. And here T2 will be, sorry, T1 will be common. So the next process, next step. Here T3 is taken out, here T1 is taken out. T1 and T3. Here is the network output in terms of T1, T3, pressure ratio, and specific heat ratio. Now, what I want to find out, that point where derivative or slope of this curve with respect to RP becomes 0. W net 0. So it means you need to differentiate this equation with respect to RP and put it equal to 0. Okay. So it means this T3 is a constant, T1 is a constant. So you can write this equation as CP is also a constant. So it is actually d of W with respect to dx is equal to a constant A into another constant B. I'm representing RP as X. RP as X with the term which you used to see in your mathematics. So I'm writing in a mathematical form. A constant, another constant into 1 minus 1 over x to the power another constant C minus another constant D into x to the power same C minus 1. A, B, C, D are constant and x is a variable. You can put it in MATLAB. Okay, so that's how we can solve it. Okay. Here what he is doing, he is taking this whole term as x, making things easy. RP to the power k minus 1 over k, take it whole as x. Then this equation can be written like this. Now take integral d of, sorry, not integral, derivative with respect to x. So what will be derivative? PP is also will be like this. So first you will take with T3, that will become 0. Then T3 here is also, and what is the derivative of this thing? Negative 1, x to the power minus 1 minus 1, right? Right. Then there will be this minus also. Okay, this minus will cancel with this minus. This will become 1 over x square. This part. Then here, it will be simply T1 derivative, and the other, this is 0. So it's, and put it equal to 0. Okay, that is done here. From here, I am interested to find out x, which is this thing. So now write this equation in terms of x. This Cp will become 0. So we can write x. This will be x. And what is x? So put it x is equal to Rp to the power k minus 1 and take this k minus 1 over k on the other side so that I will have this pressure ratio equation. Here is the final equation. So what this equation is telling us, for a given T maximum and for a given T minimum and for a given type of gas, this is the optimum pressure ratio for maximum net. Similarly, you can derive another equation, Rp for efficiency. Whatever Rp comes for work and efficiency, choose anywhere between these two. This is fixed, then this should be the pressure ratio given by this. So for air, K is equal to 1.2. Just put values for T maximum, T min. So this will be the optimum pressure ratio to get maximum work. Any question? So far we have discussed ideal. Actual will be non-isentropic compression, non-isentropic expansion. Pressure drop in the heat transfer process, heat addition, and there will be pressure drop in the heat rejection processes. In this chapter, we are okay. Based on this, we can solve this simple numerical problem, which we did in Thermo 2 also. I will quickly go through. It's a simple cycle. Constant CPs for this and constant CP for this is given. Take CP this and gamma this for compression. A different CP and a little different gamma for expansion process. Okay. Isentropic efficiencies are also given. It should not be 10 to 15% higher. It must be in this range. For a newly built turbine, if you do an experiment, and if you compare it with the ideal one, there will be a difference of more 10 to 15%. Right? If you are using proper bearing with as less friction as possible, so it should be in 10 to 15%. That's how we know from experimentation. For both, because here the purpose is work transfer, mainly work transfer. The heat production should be as small as possible. So that is in our hand how by using proper lubricant, the amount of heat which is produced due to friction should be kept as minimum as possible. So it should not be more than 10 to 20%. That's the typical value which we have. Okay. But if you can, and if you are using proper maintenance, then this will be in this range, 10 to 15%. If the maintenance is not proper, you are not changing this lubricating oil just in our cars, this isentropic efficiency will continue to drop. Right? To keep it in this level, so we have to do proper maintenance.
It's not
No, yeah, it's based on experimentation. You can do a theory, then there is this tribology. It's a subject which deals with this thing. Tribology. It's all about lubrication. It's totally related to this thing. So then the theory is there. We can develop a theory. It is offered as elective courses in many universities. If you have a relevant faculty available, so that's you can learn this theory. Hmm? Ah. No, no, no. I will be teaching the same too. Okay. No, today's attendance is not working, unfortunately, or fortunately. Fortunately. No, for those who came for this, for them it's unfortunate. It's not working today. The app is not working. Now it's working. In the first class, it was not working. So now it's suddenly working. So let's make it. Okay, let's do this problem. Simple Rankine cycle, sorry, Britten cycle, isentropic efficiencies are given. That's why you have to show isentropic and non-isentropic for compressor and for turbine. Okay. Find out what we have to find out: cycle efficiency and back work ratio of that plant. So means 1 minus Q out over Q in, and back work ratio is work of compressor divided by work of turbine. So it means I need to find out 1 minus what is Q out in this case? PP actual P3 over CP into, now here CPs are given, they are different. CP into what is Q in T3 minus T2. Two actual. So in steam power plant, we used to calculate enthalpies at every point. Here, temperatures. When CP is given, now you need to find out temperature. I'm not sure he's taking this CP separate and these two CPs separate. But what about 4:1? I'm not sure. 4:1 is taken as this one as compression or as gases. We'll see. So temperatures, T1 is given. T3 is given. We need to find out T2A and T4A. So it's simple. What is this process? Isentropic, ideal gas. This is compression process. Use K for compression, which is 1.4. So find out T2S. Then isentropic efficiency of compressor, which is given by isentropic over actual. CP will cancel because here we have same CP. So from here we can find out T2A. This procedure is clear because we already did in thermo 2. That's why I'm not going into much detail. And also you from refrigeration air conditioning we use it. Same. So 3 to 4, T3 over T4, 4S. So same procedure for this case and find out T4A. Okay, using isentropic efficiency of turbine. Then we can find out efficiency, network, Q in, whatever we want. So here are the temperatures. Now finally efficiency of the isentropic efficiency of turbine will give us 4A. Work of turbine, just put values, work of compressor, CP into T2 minus T1. Just see here the work of compressor and work of turbine. We are taking 1 kilogram of mass, that's why you see kilojoules per kilogram. Okay, although total mass is given. Where is total mass is given? But to calculate efficiency, there is no need m dot. But if you want to find out total power, then m dot into H3 minus H4A. That is the power of turbine. So multiply with m dot. That will give us the total power of turbine. But here you see the difference between turbine work and compressor work. Compressor is consuming a lot of work. 382, 401 is the net, the total work output of turbine. So a significant, more than 50% is going back to derive the compressor. Okay, because it is simple turbine, that's what we will try to increase. That's why efficiency is so low, only 18%. So there are methods, again, reheating, regeneration, multiple compressors with intercooling, all these will come into play to increase this efficiency. Okay, so similarly, back work ratio is also a very large value. A significant amount of work is going back to derive compressor. And work ratio is the other way around, net work output divided by turbine work, only 18%. The total work, and after sending to the, sorry, this is the net work after sending to the compressor, network output divided. So work rate, same thing, but back work, I think, is also back work. I just calculated work ratio.
Why they don't use external source to produce?
To produce
To operate the compressor.
external source, what is that example? Some other power plant, okay. Okay, I stop here. So in the tutorial class, we'll solve that one more numerical. Yes, we can finish. So both sections at 320, right? Both sections at 320. Others may join. It's recorded.